Welcome student. 5-membered and benzo-fused 5-member heterocycles. After a long time we will going to have a little discussion on this heterocyclic compound oxazole, benzoxazole and isoxazole. These are the three molecules which we are going to discuss today. I am Dr. Devangar Pandya from Department of Chemistry, St. Javiers College, Autonomous, Ahmedabad. Let's begin with the introduction. Oxazole is a 1,3-azole having an oxygen atom and a pyridine type nitrogen atom in 3 position in a 5-membered ring. This compound first introduced by Hans in 1887 and synthesized in 1947. So you can understand how much big gap between 1887 to 1947. The benzo-fused derivative of oxazole is known as benzoxazole. Oxazole does not occur in nature, and hence there is no any fundamental biological metabolism observed as when we compare it with imidazole or when we compare it with other 1,3-azole like thiazole, etc. So there is no natural occurrence of this compound, hence there is no fundamental metabolism of this compound of this 1,3-azole. So that way it will little bit different than the other. Partial reduced oxazole is called 2,3,4-oxazoline, either 2, either 3 or 4 oxazoline. On the basis of the position of a double bond, 3 type of oxazoles are possible, which already we have said, 2 oxazoline, 3 oxazoline or 4 oxazoline, and these are the structure. This is the structure of oxazole, and as you know, when 2 heteroatom is there, numbering starting from the higher priority atom, that is oxygen. So 1, 2, 3, 4, 5. That is the way over here in benzoxazole or benzo-fused oxazole as well. 1, 2, 3, 4, 5, 6, 7. And for this semi-saturated or we can say semi-unsaturated heterocycles where 2, 3, 4. That means this is the position. After 2 double bond is there, after 3 number double bond is there, after 4 number double bond is there, and this is a completely saturated compound oxazolidine. Physical property: oxazole is a liquid compound having boiling point 69 degrees centigrade and has an odor like pyridine. Mixable with water and many organic solvents. Weakly base and having pK value 0.8 but more than oxazole. So when we compare and contrast isoxazole with oxazole comparative to isoxazole, oxazole is going to be a little weak basic in nature. The dipole moment is 1.5 dBi, that is fairly enough to make it soluble with water. That means very polar compound it is. Oxazole having a sextet of pi electrons, yet its property stated that the delocalization is incomplete but has a little aromatic character. So it's not a completely aromatic but have a little aromatic character as well. Chemically, oxazole function as dienes in the Diels-Alder reaction and electrophilic substitution reaction. Most important property, chemically oxazole has function as dienes, not an aromatic compound, in Diels-Alder reaction as well as in electrophilic substitution reaction, and it is very rare. That property can be utilized for the further application. And now synthesis from ethyl alpha hydroxyketosuccinate. Oxazole was first prepared by Confroth, and hence this synthesis of it from ethyl alpha hydroxyketosuccinate is also known as Confroth synthesis. It's a long reaction sequence. A simple method has been reported by Bredrek and Bengrit. It involves a reaction between ethyl alpha hydroxyketosuccinate and formamide to give diethyl oxazole, that is 4,5-dicarboxylate, which is subsequently hydrolyzed and decarboxylated to oxazole. Here is the reaction. We have this diesteri group treated with this amine derivative, and we're going to get at 100 degree temperature, we're going to get oxazole derivative. On hydrolysis with BaOH twice H2O, we're going to get this intermediate, and treating with quinoline in presence of copper, we're going to get our oxazole, and this is a pure oxazole, no substituent group would be there. So that is the way we can prepare artificially oxazole. Let me remember you, oxazole cannot be obtained naturally, it can be synthesized in this way. Robinson-Gabriel synthesis, different way of synthesis would be there. This method involves alpha acyloaminoketone, which undergo cyclization and dehydrogenation in presence of phosphorus pentoxide or a strong mineral acid. So here diketone, diaminoketone is there, alpha acyloketone we can say, and treated with any mineral acid, we're going to get this derivative, then water molecule depart, and we're going to get our substituted oxazole. This synthesis is applicable for the formation of 2,5-diaryl oxazole. 2,5, this is second position, this is 5 position, so two side R1 and R2 would be a phenyl group, so 2,5-diaryl oxazole can be prepared by this Robinson-Gabriel synthesis. Now synthesis from isocyanides, reaction from alpha methylated isocyanide with acid chloride or anhydride yields a substituted oxazole. A number of variations of this method have been developed by Van Leusen. So it's also known as Van Leusen synthesis, where you can see here alpha methylated isocyanide is there, treated with normobutyl lithium. So lithium derivative is going to be obtained, treated with acid chloride. We're going to get this arrangement. Then the cyclization take place by substitution of hydride. We're going to get this, and on rearrangement we're going to get our substituted oxazole. Synthesis from alpha amino carbonyl compound. This method consists of refluxing an alpha amino carbonyl compound with an amino ester to give an oxazole. Mechanistically, the amino ester first adds to the carbonyl compound in presence of acetic acid, then ring closure reaction result in the oxazole formation. So here you can see that we have alpha amino carbonyl compound, and that is treated with this ester. So the lone pair electron shifted over here, pi electron shifted on this, and we're going to reflux it in presence of acetic acid. We're going to get this intermediate, where the electron from nitrogen lone pair electron shifted over here, releasing one proton from this two formation, will ammonia released, and we're going to get this on cyclization. We're going to get this intermediate, then the proton shifted over here, we're going to get our oxazole derivative. Now synthesis from acyl aziridines. The thermolysis of one substituted 2-aryl 3-phenyl aziridine gives rise to 2-aryl 5-phenyl oxazole in a high yield. This reaction probably proceeds via azomethane ylide obtained from the heterocyclic cleavage of the carbon-carbon bond. Ylide is a compound which contains positive negative charge simultaneously. The resulting ylide cyclizes to oxazoline, which on oxidation leads to derivative of oxazole. As the reaction for that aziridine, then this lone pair electron shifted over here, so this pair of electron between these two carbons shifted on this carbon at 220 degrees centigrade. We're going to get this arrangement intermediate, where a hydrogen shifted over here and the pi electron shifted on, and cyclization take place, and that cyclization result into this one that is known as oxazoline. And on oxidation of oxazoline, we're going to get oxazole derivative. 96% high yield is going to be obtained from this synthesis. Synthesis of benzofused oxazole or benzoxazole. Benzoxazoles are usually prepared by heating 2-aminophenol derivative of carboxylic acid with various leaving group present on the acid itself. Condensation of these two substances under milder condition using boric acid has been recently reported. The reaction of an ethoxycarboxyl thiamide with orthoaminophenol similarly affords to substituted benzoxazole. Here is the reaction: N-ethoxycarboxy carbonyl thiamide is there, and that is treated with orthoaminophenol phenol treated with orthoaminophenol treated with in presence of boric acid. The reflex these two compound will going to get this derivative on heating, will going to get the cyclization over here, and the oxazole benzoxazole is going to be obtained. Synthesis of benzoxazole. A treatment of N2-hydroxylphenylthiamide with superoxide O-2 at room temperature in dry acetonitrile results in the formation of two substituted benzoxazole in excellent yields. Here you can see with superoxide we are going to get benzoxazole derivative. More synthesis, superoxide are the electron reduction product of bimolecular oxygen. They have potential of acting on a redox agent, nucleophile or base. And the indoxazine photochemically rearranged to benzoxazole as well. Here indoxazine photochemically rearrange itself into oxazole. Now chemical reactions, electrophilic substitution reaction for benzoxazole. Oxazole is more reactive towards electrophilic substitution. Already we have briefed out electrophilic substitution reaction and Diels-Alder reaction. Oxazole acts as a diene, and compared to thiazole it is more reactive towards electrophilic substitution and less compared to imidazoles if we compare and contrast the compound. The preferred attack, as in the case of the 1,3-oxazole, take place at the 5 position. So 5th position is most favorable for the electrophilic attack. Electrophilic attack, however, occurs readily when the ring is activated by electron donating substituent group which already present on the oxazole ring. Bromination of 2-phenyloxazole results in 5-bromo-2-phenyloxazole. Nitration of this compound furnishes para-nitrophenyloxazole. Nitration and sulfonation of oxazole itself are difficult because of the presence of pyridine type of nitrogen on oxazole. Oxazole are mercurated in acetic acid and mercuric acetate, and the ring position react in order 5 is most favorable, then after 4, then after 2nd. Now reaction with nucleophile reagent. Nucleophilic substitution reaction on oxazole ring are uncommon. There is very less reaction available. The ease of displacement of halogen on the oxazole ring is C2 पे अगर होगा that is substituted more displaced more rapidly than C4, and then it is less, because as you know C5 is a very most favorable position for the electrophile, so to remove electrophile from C5 is little difficult and it would be easy from C2. The cleavage of the oxazole ring by nucleophiles is rather a more frequent reaction than nucleophilic substitution reaction. Here you can see treating with ammonia, the oxazole derivative as a nucleophile is going to attack on this carbon. So the electron shifted on this, so the ring opening reaction take place in presence of ammonia. Further when we react, we are going to get diamino derivative. Then dehydration take place and we are going to get this diamino derivative, which on cyclization gives our imidazole derivative. Diels-Alder reaction, as you know, oxazole is most that means reactive for Diels-Alder reaction and act as dienes as well. The introduction of a second heteroatoms does not affect the diene nature of the oxazole as well. Oxazole behaves similar to furans in Diels-Alder reaction. The adexo obtained on the reaction with dienophiles are important initiator for the preparation of pyridine or furan derivatives by loss of appropriate fragments. Here is the reaction. We have our oxazole derivative treating with this diester. We will going to get this intermediate, and then further it will going to give this pyridine or furan kind of derivative. A reaction with oxidizing and reducing agent. Oxazole ring is opened by the action of the oxidizing agents such as cold camphor, chromic bromide, or ozone. Oxazole is stable with a weaker oxidizing agent like hydrogen peroxide. Oxazole are remarkably stable towards a variety of reducing agents. Catalytic hydrogenation has been achieved with platinum oxide. Here you can see it is stable towards this milder oxidizing agent, and with lithium aluminum hydride in presence of THF, ring opening reaction take place, and we're going to get this catalytic hydrogenation of this compound. Naturally occurring or biologically active compound. Occurrence of oxazole in nature is rare. We will not found oxazole in nature. It can be synthesized in laboratory. It is the alkaloid pimperinine isolated from Streptomyces pimperina biological species. Oxazole derivatives are known to have anti-inflammatory, analgesic, antibacterial, and antiviral property, and as a result of that, it is biologically most important molecule. Two amino azoles are useful as hypertensive agent as well. So you can see more biological property oxazole possess. Oxazole derivative possess antibiotic activity as well. These are certain familiar molecule of oxazole which is readily available as medicine and utilized as a antibiotic agents. Isoxazole. Isoxazole, the oxygen and nitrogen present at 1,2 relationship, and the compound first obtained in 1903. Two classes of benzofused analogues exist: benzisoxazole or 1,2-benzisoxazole, or endoxazine and 2,1-benzisoxazole, or anthranil or benzisoxazole. These are certain similar name of the same compound. Certain isoxazole derivatives are known to possess anti-tuberculosis, analgesic, and local anesthetic activities. The dihydroderivatives are called isoxazoline, which such as 2-isoxazoline and isoxazolidine. So these are all the molecule which we have discussed. One is isoxazole, starting from 1, 2 position, and then 3, 4, 5. Benzisoxazole, 1,2-benzisoxazole or anthranil, or it is also known as benzisoxazole, benzofused derivative. 2-isoxazoline, that is semi-saturated, and completely saturated, that is isoxazolidine. Now, physical property of the compound: isoxazole is a liquid boiling point 95 degrees centigrade and disables to pyridine in odor. It is a very weak base, pK value 1.3 like pyrazole. So comparing with pyrazole, it is a weak base and it is not dissolved in a weak acid. Isoxazole nucleus is considerably less aromatic than 5-membered heterocycles, including oxazole and furan as well. Isoxazole is best represented as a resonance hybrid of several resonance structures, and prototropic tautomerism of isoxazole derivatives such as isoxazole 5-ons exist in 3 tautomeric forms. It has dipole moment 3.3 dBi like benzene, so unlike benzene, so most polar molecule it is and gets soluble in water. Now, synthesis from diketones. The most general method for the synthesis of isoxazole involves the condensation cyclization of alpha beta with hydroxylamine equation. So diketone is there with hydroxylamine. We are going to get the derivative. These two derivatives going to be obtained. The reaction involves an initial attack of hydroxylamine on the carbonyl carbon, which on subsequent cyclization yield a mixture of isomeric isoxazole. Now, synthesis from diketone again. The use of acetyl derivative of 1,3-dicarbonyl compound is important. 1,1,3,3 tetra alkoxyl alkanes are readily available and react with hydroxylamine. For instance, 1,1,3,3 tetra ethoxypropane on reaction with hydroxylamine yields the parent compound. As the reaction, very simple isoxazole formation is there and non-substituted simple molecule is going to be obtained. Again from diketone, Quiloco and Kovacus describes an unequivocal synthesis of substituted isoxazole from ketone oxime having an alpha hydrogen and an aromatic ester. Thus from acetophenone and phenyl acetate isoxazole, that is structure 42, is going to be obtained. The isoxazole have been obtained from enamines as well. Here is the reaction with butyl lithium. When this compound treated, we're going to get this dianion. On treating with ester, we're going to get this. On cyclization, we'll obtain this derivative, and on loose dehydration, we're going to get isoxazole derivative. From gamma pyrons, a nucleophilic attack on the gamma pyron ring system usually proceed through ring opening followed by recyclization to afford various heterocyclic compound. Using that strategy, a scattered example of oxime formation have been reported because of the difficulty in differentiating pyron oxime from isomeric isoxazole derivatives. For example, the reaction of flavone, that is structure 43, with hydroxylamine was earlier reported to be the oxime, that is structure 44, but a reinvestigation of this structure showed it to be the isoxazole, that is structure 45. Here is the reaction on treating with NH2OH. We're going to get these two, but initially it is assumed that this structure would be there. Then the systematic investigation stated that it is isoxazole derivative. Chromone, that is structure 46, also gives isoxazole, that is structure 47, and not oxime on treatment with hydroxylamine. Here is you can see in the equation. It may be stated that certain alpha beta unsaturated ketoxime also cyclize to isoxazole in presence of palladium complex. So here the treatment chromone, that is 46, treating with NH2O is going to give you isoxazole derivative structure 47. Thus, structure 48 on treatment with sodium phenoxide and dichlorobis tetraphenyl phosphine palladium in dry benzene on refluxing gives structure 49, that is isoxazole derivative. From nitrile oxide, isoxazole are generally prepared by cyclidation of olefin or acetylene to nitrile oxide. The treatment of chloroxime, that is structure 50, with base, particularly with triethylamine, this is E, typological mistake, is the most commonly employed method for the preparation of nitrile oxide, that is structure 51. So on treating with this chloroxime, with base, we're going to get this structure 51, that is nitrile oxide, and that we are going to use in the synthesis. Nitrile oxides such obtained that react with a monosubstituted alkyl or aryl alkyne selectively via 1,3 cycloaddition to yield 5 substituted isoxazole. Rhizoselectivity means treating with one of the element of different functional group. Specifically, that is called rhizoselectivity. So here you can see rhizoselective reaction, and we're going to get isoxazole derivative from nitroxide. The synthesis proceeds in 2 stages. Here is the mechanism. The reaction of nitrile oxide with alkene containing a leaving group with which leads to elimination is rather facile, and the reaction is stereospecific with respect to the alkene whose geometry in preserved in the product. The addition is also rhizoselective, but not always so. Vinyl halide react with nitrile oxide, afford 3 substituted oxazole. Fuminic acid with vinyl acetate gives 95% yield of the parent compound isoxazole. You can see the reaction over here. Recently, O-trimethylsilyl acetohydroxyl hydroxymoyl chloride and O-ethoxycarbonyl hydroxymoyl chloride have been used, which leads to a nitrile oxide on thermolysis. The resultant nitrile oxide can be trapped with an alkyne to the corresponding isoxazole. Benzisoxazole, benzofused isoxazole. Endoxazine may be obtained from O-halogenobenzoyl compound and hydroxylamine in presence of a base. So this O-hydrogeno compound, orthohalogenobenzoyl compound, and treating with hydroxylamine will going to give this intermediate, and treating with base substitution of proton and bromide will going to get the 3-phenyl benzisoxazole. The thermal decomposition, it's a typological mistake. Thermal decomposition of salicylaldehyde acetyloxime produce an unsaturated endoxazine in this equation. Benzoxazole reduction in presence of zinc acetic acid CS3COOH, here 3 is missing, of orthonitrobenzoyl compound furnishes the corresponding anthranils. Steam distillation of the glycidic acid, that is structure 52, proceeds with the elimination of water and carbon dioxide to give 3-formyl anthranil, that is structure 53 in this equation. Chemical reaction. Electrophilic substitution of 1,2-azole are generally much less reactive than 1,3-azole. So if we are going to say compare isoxazole with oxazole, isoxazole is little less reactive compared to oxazole. Isoxazole are more reactive than isothiazoles but less than pyrazole. These are comparative relation between the different oxazoles. The electrophilic attack occurs readily at carbon 4 and frequently fails if this position is occupied. But the heteroatoms influence the rate of electrophilic substitution in isoxazole ring. Because of the electron withdrawing nature of the nitrogen atom, the electrophilic attack is retarded in pyridine. The electron donating property of oxygen atom, on the other hand, facilitates such a reaction. Isoxazole derivatives are chlorinated or brominated with free halogen on heating, and bromosuccinamide also brominates to give 4-bromoisoxazole. Nitration with HNO3H2SO4 of nitroisoxazole according to 5-methyl-isoxazole gives 5-methyl-4 derivative in the following mechanism. Sulfonation of isoxazole has been relatively less investigated than the nitration. Aryl substituted isoxazole on chlorosulfonation tend to give product of homocyclic ring sulfonation rather than isoxazole ring. Isoxazole display no reactivity in the Friedel-Crafts reaction or Walsmia formylation. Benzoxazoles undergo electrophilic substitution exclusively in aryl ring. Here is the reaction nitration process. With nucleophilic reagent, isoxazole is labile towards the nucleophilic attack or strong base. This makes the chemical behavior of isoxazole fundamentally different from the pyridine. Chichi-Babin reaction fails in case of isoxazole as it opens up the isoxazole ring. Reaction involving displacement of halogen at carbon 3 or carbon 5 position in isoxazole are known. Strong base results in the cleavage of isoxazole ring yield yielding beta keto nitriles as the end product. Here is the reaction for that. Now reduction with sodium ethanol CH3OH3 is missing over here, or any nickel of isoxazole normally leads to ring cleavage. The cleavage of nitro-oxygen bond take place and it appropriate functional group are present, then the new ring are formed by intermolecular reaction as well. This is illustrated in this example. Here you can see treating with H2 in presence of nickel. You can see ring opening reaction take place and then recyclize to pyridine. In contrast, isoxazole ring system is stable to many oxidizing agents, though not in alkali medium. Condensation involving methyl group. A unique feature of picoline and many azoles is the familiar reaction of the methyl group to undergo condensation of the aldol type. Alkyl isoxazole respond to such reaction. The methyl group should be at carbon 5 and not at carbon 3 is more reactive. Thus 3,5-dimethyl isoxazole condense with the benzaldehyde to give 3,4,3-methyl for benzyl methyl isoxazole. Here is the reaction of such photochemical reaction. The photochemical reaction of isoxazole have been thoroughly investigated. In many cases, azerine intermediate have been identified in the conversion of isoxazole to oxazole. 3,5-diphenyl isoxazole rearranged to 3,5-diphenyl oxazole. Here the arrangement would be there, and that is the way we can convert isoxazole to oxazole. Isoxazole also rearranged thermally to oxazole. We can exemplify it over here. Isoxazole thermally we can obtain into oxazole by this free radical rearrangement reaction, photochemical reaction. In addition, ring contraction and ring expansion products have been observed by Ullmann and Singh. Polycyclic oxazole yield oxazole on irradiation via serine and isonitrile as an intermediate for 5,6,7 tetrahydro 1,2 benzisoxazole isomerized to 4,5,6,7 tetra it is E typological mistake tetrahydro benzoxazole in quantitative yield. That is the reaction for that. You can see 99% yield is going to be obtained in this process. Cycloaddition reaction. Isoxazole behave as dinophiles in the Diels-Alder reaction in contrast to ozone which act as only dine. The 4+2 cycloaddition between ethyl 4 nitro 3 phenyl isoxazole, that is structure 54, cyclohexa 1,3-dine, that is structure 55, yields the ADACT 56. So this will going to give cycloaddition reaction and gives ADACT 56. 2,1 benzisoxazole in contrast behave as a dine. Well, this is enough from my side. Thank you for paying attention to this video lecture. Keep asking question. As you know, asking question is a beautiful way to gain knowledge. Thank you.